Uh, so the title of my talk is Stability of Schwarzschild, and I have prepared this talk in the honor of Professor Vishveshwara. Here is the man. He has been called the black hole man of India in the media. Here is a cartoon that Professor Bala also showed. The part that I liked very much is, I have a grant, therefore it must exist. So one of my favorite cartoons is this one. I can see alcohol molecules in outer space, there must be life out there. This one I liked. Okay, so Professor Vishveshwara made very important contributions to the subject of general relativity, and most notably to the subject of black hole perturbation theory. He gave the concept of quasi-normal modes. It's a great honor for me to be presenting this talk, highlighting his contributions. His popular science book, Einstein's Enigma or Black Holes in My Bubble Bath, is widely acclaimed. I came across this book in Borders in Santa Barbara during my PhD days, and I was very inspired that an Indian author is selling in the US in the popular science section, so that was very inspiring for me. I did not know at that time contributions of Professor Vishveshwara. So a book titled Black Holes, Gravitational Radiation and the Universe, Essays in Honors of Vishu, edited by Bala Iyer and Biplav Bhawal, is published in '99. Many famous physicists, Roger Penrose, Bekenstein, Ashtekar, Ashok Sen, have contributed essays in that book. So I met Professor Vishveshwara only once at IIT Kanpur in 2008. I was visiting India during that time in the final stages of my PhD, and we were staying in the guest house. He spoke to me fondly about his work on stability of black holes and about Chandrasekhar. He was very fond of Chandrasekhar. He gave me a copy of his article from Current Science about Chandra. I was trying to explain to him my work with Henrietta Alwang and Roberto Amparan on the stability of black rings. He was very interested in listening to me, despite his old age and esoteric nature of the subject. This work is really in 5 dimensions for non-spherical horizons, and the object that we were studying is unstable, but still he showed a lot of interest in this work. Afterwards, I had a conversation with Roberto Amparan about my interactions with Professor Vishveshwara, and he told me that Professor Vishveshwara visited Spain. He had a visiting position in Spain, and Roberto had heard a colloquium on black holes from him, and he had similar conversations about this. Okay, so here is the outline of my talk. I will give an introduction, then I will try to put Vishveshwara's work in a historical context. That means really I have to give a primer in black hole perturbation theory. Then I will discuss quasi-normal modes, and time permitting I will talk about modern developments and legacy. So the talk is somewhat technical. I hope, please feel free to stop me for questions. Okay, so stability of black holes and the subject of black hole perturbation theory is a topic of much interest. It has astrophysical interest. It has interest in ADS, CFT and holography. This subject features in discussions on near equilibrium properties of strongly coupled gauge theories. It has intriguing connections. It highlights intriguing connections between black hole horizons and hydrodynamics and so on. The subject also features in gravitational wave astronomy. Ring down plays an important role in the dynamics of merged black holes, and perturbation theory is used to infer mass and angular momentum of these black holes. This topic goes on and off. So quasi-normal modes have been thought of as a bridge between classical and quantum gravity, but the discussion comes up on the archive, and then after a few months it dies down. So it remains a question mark, but the quasi-normal modes and the black hole perturbation theory in general has been thought of that it can provide some bridge between classical and quantum gravity. Okay, so birth of quasi-normal modes. The early 70s was a confusing time for black hole physics. Before the concept of black hole was introduced and popularized by John Wheeler, Vishveshwara was studying scattering of Gaussian wave packets numerically of the Schwarzschild black hole. In 1970, he noticed that waveforms at later time consist of damped sinusoidal oscillation with ringing frequency independent of the parameters of the Gaussian wave packets. And this was really the discovery of quasi-normal modes, and the subject of quasi-normal modes was born. Uh, in the year after this work, a group in 71 also noticed similar phenomena where they modeled radial infall of particle in Schwarzschild black hole, and they did this using black hole perturbation theory. So this result sort of tied up with this, and this confirmed the quasi-normal modes story. Okay, so here, so this was by Press and Tukowski perhaps also, but Press certainly. Okay, so here are the milestones in the development of this subject. In 1957, Regge and Wheeler analyzed a special class of gravitational perturbations to Schwarzschild geometry. This marks the birth of black hole perturbation theory, but the issue of boundary conditions was not clear. And also they were using the Schwarzschild coordinate, which had a singularity, so the nature of the singularity and the features related to horizons were also not clear. In 10 years, Wheeler understood the boundary conditions and he coined the term black hole. In 1970, Zerilli extended the analysis of Regge and Wheeler to general perturbation. Regge and Wheeler were studying only special class of perturbations. Zerilli studied most general perturbations. And in the same year, Vishveshwara studied those perturbation equations numerically. In 75, Chandrasekhar and Detweiler computed numerically some quasi-normal modes based on the Zerilli and Regge-Wheeler potentials. And they showed that the Regge-Wheeler and Zerilli potentials, although the potentials are very different, they are isospectral. They have exactly the same spectrum. In 1983, Chandrasekhar's book on black hole perturbation theory came out. This sort of set the notation and trends and things like those. In 89, it was shown that ring down based test of no error theorem of general relativity are possible. In 97, the ADS CFT era began with the famous work of Maldacena. In 98, signal to noise ratio for ring down waves can be potentially larger from signal to noise ratio for the in spiral wave was noticed, and this was noticed for both LIGO and LISA experiments. And this sort of highlighted that quasi-normal modes are more important than you might have thought. In 1999, Horowitz and Hubany computed quasi-normal modes for ADS black holes. In 2002, quasi-normal mode spectra was shown to correspond to poles of the retarded correlation functions from ADS CFT. In 2005, Pretorius achieved numerical simulations of black hole binary problem, and the waveform that he computed indicated that the ring down contribution is substantial in terms of the radiated energy from such a process. And from 2006 to 2010 onwards, there has been a lot of studies about low-lying quasi-normal modes, its relation to fluid gravity correspondence, its relation to black hole membrane paradigm, and so on and so forth. I will say about the modern developments towards the end of my talk. So the key point is that black hole perturbation theory has given numerous physical and technical results. It has found numerous applications, many mathematical physics results, and it's a subject of startling complexity and richness. Okay, so now let me give a little more technical introduction to this perturbation theory. So consider scalar field propagating in the Schwarzschild metric. We can decompose this scalar into spherical harmonic modes, and if we define this potential psi of r, which has this 1 over r here, then one can show that this equation becomes just the Schrodinger equation. So the variable psi satisfies the Schrodinger equation, where r star is the so-called tortoise coordinate, and r star goes to minus infinity at the horizon, and r star goes to plus infinity. So this is the place where Bala was mentioning that Vishu was interested in quantum mechanical problems. So because the perturbation theory problem can be converted into a Schrodinger equation, the connection to quantum mechanics is very natural. And this happens, in fact, for all sorts of perturbations. And I will show now how this happens for the gravitational perturbations. So now consider gravitational perturbations. So this is the Schwarzschild metric, and you perturb this by some small perturbation h mu nu, and you take the perturbation h mu nu of the form e to the minus I omega t h tilde h mu nu. After appropriate gauge fixing, and this gauge fixing is called Regge-Wheeler gauge, perturbations fall into two classes, odd parity and even parity. But the important thing is that for both these cases, the perturbation problem reduces to a Schrodinger equation. Yeah, so this is the so Regge-Wheeler class. So this is the Regge-Wheeler class of perturbation that they studied in their paper. So this is the easier class of perturbation. They are odd parity because they have this special profile of the spherical harmonics. And the gauge is really that one can bring so R T R theta phi. One can bring these components to zero by a gauge transformation. And these are the only two variables which are left in this h mu tilde. Okay, so now these authors were able to make a very clever choice of variables. So when you substitute this into Einstein's equations, you get three coupled ordinary differential equations. But these two variables can be combined into a single potential psi minus, and the combination is like this. So H1, which appears here, is directly related to psi minus through this multiplicative factor, and H0 is related to psi minus through this derivative, and this is consistent with the Einstein's equations. And once you do this, then the psi minus also satisfies the Schrodinger equation. So the key point is that this is what Regge and Wheeler were able to do. By appropriate choice of gauge fixing and choosing the right set of variables, they were able to reduce the problem of gravitational perturbation for odd parity to one Schrodinger equation. Okay. So in 1970, Zerilli looked at the much harder case of even parity perturbations. So even parity case, one cannot put those things to zero. Those things have to be there, and the spherical harmonics appear like this. So this gave rise to 7 coupled ordinary differential equations, and Regge and Wheeler were not able to make progress on this. But Zerilli found a variable psi plus, and he was able to show that using various combinations of these functions and so on, one can again reduce the problem to the Schrodinger equation. So although the psi plus and psi minus are very different, V plus and V minus are very different, Chandrasekhar and Detweiler were able to show that the two potentials are isospectral. So if you compute quasi-normal spectrum through this equation or through that equation, you will find that the spectrum is identical. And they were able to prove this because they found a very complicated transformations of variables which change psi plus to psi minus and V plus to V minus. Okay. So in this discussion, Vishveshwara contributed in several important ways. I will highlight only two such points. So in a well-known paper, he fixed various typos in the Regge-Wheeler analysis because he was interested in doing a numerical study, and for the numerical study, the equations have to be really very correct. And as I think this was one of his earliest paper during his PhD days. So with Edelstein, he looked at Regge-Wheeler analysis in more detail and fixed several typos in this. So as I mentioned, although V plus and V minus are very different, Vishveshwara observed their isospectral nature in his numerical analysis. So when he was doing these numerical calculations, he found that surprisingly, he is finding the same spectrum. So Chandrasekhar et al. Showed later that the two potentials are isospectral, but they acknowledged CVV in a footnote. They said that Vishu has also observed this, although in a numerical work, but we are able to show analytically that there is a transformation which maps V plus to V minus. But his main contribution was the idea of the quasi-normal modes, and this is what I will discuss now. Okay, so quasi-normal modes. So there is a conceptual understanding. So Schwarzschild solution falls into the so-called algebraically special class of solution. And for algebraically special solution, there is a now general theorems that the even and odd parity perturbations are isospectral. For Kerr is also algebraically special, but not in the same class. I don't think for Kerr there is such a result. But for Kerr, actually, I don't know, because the variables are also very complicated. And Schrodinger, this seems magic to me. I don't have a good answer. In fact, in all cases, spin-s perturbations in ADS, all cases it reduces to a Schrodinger problem. And yeah. Okay, so quasi-normal modes. So quasi-normal modes is an eigenvalue problem for that Schrodinger equation. And this is natural solutions to the unforced ordinary differential equation that I showed. And in order to solve these equations, one has to impose boundary conditions at the horizon and at infinity. And for most spacetimes of interest, the potential goes to 0 at the horizon. In fact, for the Schwarzschild case, it goes to 0 exponentially, faster than exponential at the horizon. So natural boundary condition is that classically nothing leaves the horizon, that is the purely ingoing boundary conditions at the horizon. So one puts e to the minus I omega t plus r star as r star goes to minus infinity. So this is like going at the horizon, and this is like saying that you have only ingoing modes at the horizon. Okay, for asymptotically flat space-time, the potential is 0 at infinity. So it's natural to put purely outgoing boundary conditions. So we discard unphysical waves which are entering the space-time from infinity, and that's why we put purely outgoing boundary condition. This means that e to the minus I omega t minus r star. So note the difference as r star goes to plus infinity. Okay, so with these boundary conditions, one can try to solve the Schrodinger equation, and one finds that quasi-normal modes generically have real and imaginary parts, and the modes depend on angular momentum quantum number L and M, and you generally find discrete family of these solutions, so there is this overtone number N. Okay, so one finds in almost all cases infinite number of such solutions but countable, and we organize them in the following way. So we say that as N increases, the absolute value of the imaginary part of omega increases. So N equal to 0 is the least damp mode, and as N increases, the damping increases more and more. And the lowest mode is at N equal to 0. Okay, this is just a convention, like how you start this counting. So we start the counting at N equal to 0, where the imaginary part is the lowest. Okay. So although this is the general problem that one has to solve, but usually this is not so easy to solve. There are a number of issues involved in solving this. A complete mathematical theory of such an eigenvalue problem is still, in my opinion, not fully developed. There is a lot of mathematical physics work on how to compute these modes, how to play with these modes, how the spectrum is spaced and so on, but a complete theory of mode decomposition, can we write a generic perturbation into quasi-normal modes and things like those things are still not fully developed. But the stability issue can be addressed as follows. So if we can calculate all these modes, then we can set it as a criteria. The numerical criteria for stability of a black hole could be the evidence that all quasi-normal modes are damped. That is to say that the imaginary part of omega is negative in all cases. And this is what has been done for many, many black holes in flat space, in ADS, and so forth. So this is the table. Vishveshwara studied this problem for the Schwarzschild case in 1970. These two famous relativists, Monsrev and Alexeyev, they studied the problem in the Raison-Nordstrom case. So they studied electromagnetic and gravitational perturbations, and they were able to reduce again the problem to the Schrodinger equation. For extreme black holes, the problem was open for many, many years. And this mathematician, Aritakis, has shown that extreme Raison-Nordstrom black holes are actually unstable. And I will argue, if I get the time, why this is the case. For Kerr black hole, for non-extreme Kerr black hole, Pless and Topolsky did this marvelous study in 73 and 74. They are very famous for this study. Again, for extreme Kerr, the problem was open for many years, and only very recently, Luchetti and Rial have addressed this question, and taking ideas from this paper, they have also shown that extreme Kerr is unstable. And for Kerr-Newman black hole, still the issues are not completely settled. Nobody has shown how to decouple gravitational versus electromagnetic perturbations in the case of Kerr-Newman black hole. Okay. No. So I am talking about the outer horizon. So in the case of extreme Dyson-Nordstrom black hole, I will argue if I get the time that the outer horizon is also unstable. So
Horizon instability, transmitted to the outer horizon precisely
so
because it's
this was the
extreme.
heuristic argument given by Don Marolf that the inner horizon of Dyson-Nordstrom is unstable, so this instability can be transmitted to the outer horizon. But this was a heuristic argument. This mathematician has given a more precise argument for that.
Okay, maybe
Yeah,
we can later, but
if I get the time, I will explain what the argument is. Okay, so this is the famous paper of Vishveshwara, where he made the contributions to the stability of the Schwarzschild metric. Let me say a few things about this paper. So he contributed this PRD paper. In this paper, gravitational perturbation modes of the type e to the minus I omega t were studied. He looked at purely imaginary modes, real modes, complex modes. Boundary condition issues were fully addressed because by that time the critical coordinates were known and were widely used. And this is in sharp contrast with the work of Regge and Wheeler, where they were confused about the smoothness of the perturbations and so on. One of the key contributions in this paper was the following. So he showed that perturbations that grow in time are ruled out. That is to say, if you look at purely imaginary modes, that is omega equal to I alpha, alpha negative, then it turns out that modes that diverge at, so it turns out that the modes either diverge at the event horizon or they diverge at infinity. So if you look at the modes which fall off at infinity, then they necessarily diverge at the event horizon. And this way he ruled out the purely imaginary perturbations which grow in time. Another very interesting contribution in the same paper was that he was able to show that if there is no time dependence, then there is only one mode, that is the stationary mode, and this mode was identified to be the deformation to the curve family. So from Schwarzschild to curve, no time dependence, and one is able to find this in a perturbation theory. The third contribution in the same paper was that he mentioned that the complex frequencies are more complicated and interesting to analyze. He discussed these things very briefly in that paper and more thoroughly in his PhD thesis. What I find always very intriguing is that in the same paper he pointed out that there is a conceptual issue concerning mode stability versus stability under generic perturbation. That is to say, what does mode stability implies if you sum these modes and talk about the stability problem under a generic initial data. And this is some problem that has worried mathematicians for many, many years. And only in 2016, these three mathematicians have given a complete proof of linear stability of Schwarzschild solution. So Defarmas, Horzegel, and Rodinansky. So there is always the issue that, actually I wrote only one equation about the mode sum. So there is always the issue that how valid is this mode sum decomposition? Because when omega becomes complex, and if you put these ingoing and outgoing boundary condition, there is a regime which is omega I negative and R large, where QNM so in this regime, the quasi-normal mode wave functions will behave because omega is imaginary and you look at large R behavior, then the term that you get is like omega e to the plus mod omega I times R. So it's not clear whether a generic perturbation can be written as a mode sum decomposition in the quasi-normal modes. And this is an issue that has bothered relativists for many, many years. And I always find very inspiring that Vishveshwara mentioned this in this paper. And only now this issue has been completely settled. So what these authors have shown is that you look at a generic perturbation which is asymptotically flat, and you evolve this using theories of partial differential equations. They are able to show that this perturbation takes you to a curve family. It doesn't destroy the black hole. Okay. Okay, so this is also what Bala mentioned. In 1970, CVV contributed in Nature a short letter titled Scattering of Gravitational Radiation by a Schwarzschild Black Hole. In this paper, infinite redshift issues as well as the one-way membrane issues of the Schwarzschild surface were fully understood. In this paper, he studied Gaussian wave packets, scattering of Gaussian wave packets through the Schwarzschild potential, and ring down waves were observed, and the spacing in the peaks was related to the Schwarzschild mass. So I will just show the picture from his paper. It's very interesting to see that the picture that we have seen in the newspapers looks quite similar to this one, and this is in 1970. So it's very, very interesting. Okay, so now let me talk about some modern developments. I still have time. Okay, so I have chosen two topics to speak on. So first is the instability of extreme black holes. This is very, very surprising, and this is a modern development. Extremal black holes are constant source of results from quantum gravity investigations. Indian contribution has been at the forefront in this, but they have been very thorny from the classical gravity point of view. And instability of classical extremal black holes have been argued by several authors. So one heuristic argument has been given by Don Marolf, and the argument says that if you look at, so look at near extreme black hole. So it has a Penrose diagram of relevant part of the Penrose diagram like this. So this is the outer horizon, and these are the inner horizon. And we know from various numerical simulations and various work that these inner horizons are supposed to be unstable. And now let us calculate the time that an infalling observer takes to go from R plus to R minus. So this is what Don computed, and he found that time goes as like this. Some corrections. But the proper time it takes for an observer to cross R plus and go to R minus goes as R plus minus R minus. So in the limit when the black hole become extremes, it seems as if the observer has no time to travel in between. So observer, as soon as it crosses the outer horizon, is hitting the inner horizon. And this led him to argue that extremal black holes are probably unstable. And in general, like this issue has been going on, and this has bothered many relativists. But a precise argument was given by this mathematician. So Aretekis in 2011 presented a precise calculation showing that these objects are unstable. So I will try to give the argument. So this paragraph is somewhat technical. So his argument is like this. So consider initial data for the perturbation of psi which intersects the horizon. So the idea is that there is a black hole, and you put some perturbation psi which has some intersection with the horizon. So it's not completely outside, some part intersects the horizon. In that case, one can construct a conserved quantity on the horizon. That is to say, as you let the horizon evolve, there will be a quantity which is conserved as a function of v. V is the Eddington-Finkelstein coordinate. So with this constant, he showed, or it can be shown, that the derivative del r psi does not decay on the horizon. That is to say, the derivative of this perturbation remains constant on the horizon. But one can also show that the field as well as other derivatives decay outside the horizon. So everything is sort of decaying outside the horizon, but on the horizon, because there is this constant, it does not decay. And this leads to a blow up of the second derivative of psi on the horizon at late times. And this is essentially the argument that it seems that if you consider perturbations of this type, then you wait long enough, then the second derivative seems to blow up. Okay, so this analysis has been generalized to several cases and just at the horizon. Outside the, yeah, so since you have added this perturbation, people have argued that this perturbation takes the black hole to a non-extremal black hole. So at the horizon, under generic perturbation, there will be a singularity. Yeah. From outside, if you look at only the Schwarzschild time, yeah, you will not see it. Yeah. In the V coordinate, you will see the singularity. So quasi-normal modes don't, yeah, quasi-normal modes, yeah, for extremal black hole, there is a curious problem that the potential does not go to zero exponentially. So it goes to zero like power law at the horizon. And it does something here and then again goes to zero power law at r equal to infinity. And because of this power law behavior, people have attempted to define, but the analyticity property of these wave functions are somewhat complicated. But one can still attempt to define something along those lines.
From the ADS perspective, this could be more like some zero temperature case where you don't have.
Okay, so now Rajesh mentions ADS CFT. Let me say a few things about ADS. So quasi-normal modes in ADS is a topic which has attracted a huge amount of attention. I cannot do a full justice because a separate detailed discussion is required to do justice to this topic. But again, one imposes purely ingoing boundary conditions at the horizon. And boundary conditions at infinity is a subtle topic here, because unlike the asymptotically flat case, the potential does not go to zero. So potential diverges at the boundary of ADS. So for massless scalar, the Dirichlet boundary conditions at infinity is the most natural choice. And this is what relativists as well as CFT people have studied. But for gravity, for gravitational perturbation and for vector fields, there is no canonical choice. And ADS CFT dictates certain boundary conditions, but those are not necessarily the boundary conditions that people have studied in this topic. The boundary conditions that ADS CFT dictates has the following feature. So in the Lorentzian context, one can compute these quasi-normal modes, and these quasi-normal modes correspond to poles in the retarded thermal correlation functions of the CFT. And these poles precisely correspond to the location of quasi-normal modes in the bulk fields. Okay, and lowest quasi-normal modes are closely related to the hydrodynamic limit, and this is what TFR group has contributed a lot to. Okay, so questions, comments at this, because I only had two slides, one slide on ADS and one slide on extremal black hole. These are talks in themselves, but I cannot give them here. Okay, so now let me try to close with the legacy. And so quasi-normal modes of black hole spacetime contain wealth of information about classical and quantum properties of spacetime. They certainly are the criteria for the stability of spacetimes. There is always some speculation about relation to quantum properties, but this has not been completely precise. In Lorentzian ADS CFT, quasi-normal modes contain information about thermal correlation functions and hence about the spectrum and dispersions of these correlation functions. In gravitational wave astronomy, they contain information about ring down waves. They control the late time behavior of merging black holes. By now, we know a lot about linear or mode stability of various black holes and black brains, but certainly far from everything. So I just mentioned two topics. So linear stability of higher dimensional black holes is still a topic which is much under discussion. we still don't know how to separate gravitational perturbations for Myers-Berry black hole. This has been an open problem for more than 20 years, but still nobody knows how to decouple gravitational perturbations for Myers-Berry black hole. Another topic closely related is Gregory-Laflamme instability for black brains. This is a topic that keeps coming in the literature and is much discussed. There is a new topic that has come forth. This is the nonlinear stability of black holes, about which not much is known. I will say a little bit more about in the next slide. Okay, so quasi-normal modes remain an important tool in ADS condensed matter discussions, membrane paradigm discussion, hydrodynamics discussions. Now let me just say a few things about peculiar features of quasi-normal modes and end this talk. So in global ADS, it has been argued that there are very long-lived quasi-normal modes. These are modes for which omega I becomes 0, and the way this happens is that omega I at large angular momentum becomes 0. So let me just try to give you a picture how this happens. So these are this happens because there is something peculiar in ADS. This is stably trapped geodesics in ADS. So the phenomena is like this, that you have ADS space and you have a black hole here. So this is in the time direction like this. And if you consider a particle which is rotating at very large angular momentum, then because it has a large angular momentum, it cannot go inside because it has large angular momentum, so it has to remain outside. But it cannot go outside also because at the boundary there are reflecting boundary conditions. So the particle is stably trapped. Even if you perturb the particle, it does not, it has no place to go. It will remain trapped in certain region. And if you compute quasi-normal modes corresponding to this geometrical optics approximation, then one finds that omega I goes to 0, L going to infinity. So this is the sense in which Vishu's legacy will always remain because these modes will never decay, they will always remain there. So the physics of these modes and their implications for classical and quantum properties is not very well explored. The literature on this topic is very confusing, and it is not clear what these modes really mean from ADS-CFT discussions. But this whole issue is closely tied to the nonlinear stability of ADS, and understanding of this in ADS-CFT is much debated. Okay, so so this is related to this and also what Bala said. Relation between quasi-normal modes and unstable circular orbits is not fully explored. I mean, there is some understanding, but not complete understanding. But now there are solutions which have stable circular orbits. So this is an example of Kerr ADS where this happens. And very recently, Cambridge group has shown that in black hole microstate geometries also the same thing happens. At the bottom of the throat, there are stably trapped null geodesics. And there are quasi-normal modes corresponding to them. What is the meaning of these quasi-normal modes? Okay, so there is a huge mathematical physics literature on quasi-normal modes, but as far as I am concerned, it's mostly application oriented. People have come up with various techniques, various ideas how to compute these modes and how to compute the wave functions and so on. But there is no complete theory addressing topics like quasi-normal mode expansion, completeness relation, mode sum, and things like those. Okay, so clearly a lot remains to be understood, and with this I will stop.
Any questions?
Yeah, this is the, yeah. I mean, it does not look so surprising from this point of view, but when you speak to a relativist asking what is the stability property of extreme curve, everybody will say that, oh, don't worry, those are stable objects. And for extreme black holes in string theory, like because they are believed to have supersymmetric properties, everybody believes that they are stable. But this argument applies to all cases. So,
yes, Subrat.
This is the same point, but extreme black holes are stable in that from out, they don't have this instability refers to the fact that the interior is unstable. You might have thought that there's a smooth solution inside, but there isn't. This instability causes the inner horizon to develop a singularity, and so there's infalling observer dies at the horizon.
okay, yeah, very
But
good. So
outside
yeah,
it's stable.
yeah. So essentially the point is that so the inside singularity sort of comes and hits you. Yeah, this is
Exactly right.
Yeah.
I have a small question. So what is the boundary condition you will impose if you have a situation like this, when R plus is near R minus, in the differential equation?
In the differential, so in the non-extreme case, you will always impose that you have like ingoing boundary conditions here and outgoing boundary conditions
That's
here.
right.
But if you want to study just the problem in this region,
Yes.
in that case, the boundary conditions is you put 0 here and you put ingoing modes here. And this is what Chandrasekhar and Hartle analyzed in a lot of detail. And what they found is that just these perturbations blow up at the inner horizon. There is an infinite blue shift
I see.
mode.
Any other questions? So if not, let's thank Amitabh again for a beautiful talk.